Okay, so welcome to this last session for CPP this year. This session is on verified compilation, and the first talk is by Ekaterina Zhuchko. She will tell us about the formalization of extended regular expression with lookarounds using the lean prover.
Okay, thank you. So this work was part of a internship project at Microsoft Research with Margus, Veanes and Gabriel, Ebner. And today I want to talk about the formal semantics of extended regular expressions using derivatives, and we formalize it in lean. So when you start adding extended features to regular expressions, oh, yes. Is this better or no? As far as it can go. Is this better? No? Okay, this is still bad. I can just take the other. Yeah, no, that's fine. Yeah. Should I leave this one here? Okay, is this better? Yeah. Okay, right. So adding extended features to regular expressions can really create some interesting complications. Let's take this very innocent classical rule, which lifts the concatenation operation from regular expressions to languages. And already in the presence of anchors, this rule does not hold. Let's take an example of the regex A concatenated with the end-of-line anchor, and then we concatenate it with itself. Well, the language of this regex is the empty language. I'm ignoring some implementation details. But if we take the language of the individual regular expression, so A concatenated with the end-of-line anchor, the string A is in the language, so AA is a counterexample here. And a bit of context for this work is there are two papers which form the foundation of what I'll be talking about. The first one is this non-backtracking regular expression engine in .NET, which uses derivatives. But the novel idea that they implement is using location-based derivatives, unlike character-based classical derivatives. And this is done to formally handle anchors. And the match semantics here are leftmost greediest, also known as PCRE. The second work builds on the first one, but extended with some other features, most notably lookarounds. But the match semantics here are different. It's leftmost longest, also known as POSIX. And we choose to formalize the second work. So we take this paper that I mentioned, and we formalize the semantics of extended regular expressions with lookarounds, intersection, and negation, which hasn't been done before. And we also prove the correctness of the leftmost longest matching algorithm. So I will start with some preliminaries. We are working in the symbolic regular expression setting, which means that instead of working with single characters, we are working with predicates. And these predicates come from an effective Boolean algebra. It's a structure which consists of a set of domain elements. You can think of them as characters, for example. And it comes with a set of predicates, which is closed under the Boolean connectives and contains the top and bottom elements. There is also the denotation function, such that the bottom element is the empty set, top element is the entire alphabet, and then the rest of the connectives are interpreted intuitively. In Lean, we model the effective Boolean algebras as a type class, which comes with the necessary laws as fields. And It's important to mention that the denotation function is implemented as a function in the bool, which implements that the predicates are decidable. And this is where the effective comes from in the name. So we can take the domain as, for example, the standard 16-bit character class of Unicode. And then you can imagine a generic symbol from the set of predicates to be given semantics. For example, it recognizes capital Latin letters. So we're working with extended symbolic regular expressions. I explained the symbolic part. So instead of single characters, we have predicates from the effective Boolean algebra. And the extended part comes from the fact that we add the intersection negation, but most interestingly, the lookarounds. And the lookarounds express the existence of a match, but they don't actually include this information in the match as a whole. And here we have both the negative and the positive lookarounds. We also define the reversal operation on regular expressions, and this will be crucially used both in the definition of derivative, but also in the main matching algorithm. So reversal is defined in an intuitive way. The more interesting cases are the lookarounds, where the reversal of lookaheads becomes lookbacks and vice versa. I'll give a small example. If you have a regular expression, AB, concatenated with the lookahead CD, in this string, we get exactly the match AB because the lookahead condition is satisfied. If we reverse this regex, then what we get is the lookback DC concatenated with BA, and this reflects in the match. So the match is now BA in the reverse of the string. The next two concepts are going to be important for the whole development, and these are what allowed us to prove the main correctness result. Because of lookarounds, the matching now becomes context dependent. What I mean by that is, again, let's take an example of the regex A followed by B and the string ABC. So do we have a match? Well, it depends where we are in the string. So we sort of have to index the string and then peek ahead in order to check that the lookahead condition is satisfied. In order to reason about this, we introduce locations, which we model in Lean by a variant of a list zipper. So it's a pair of lists, and the first list is reversed. So for the string ABC, the initial location would just be empty list in ABC, indicating that we're at the beginning of the string. Then we could have intermediate locations, so moving this abstract pointer along the string. And the final location is just the string in reverse, and then the empty list indicating we have reached the end of the string. The reversal of a location is simply swapping the two lists, and that's nice because it's a constant time operation. Okay, so locations give us a way to place this abstract pointer, but when we talk about matching, we really want to talk about two locations. So where the match begins and where the match ends. And we do it using spans, which are now triples of lists of characters. So let's look at the example of the regex ABC and the following string. So the span view of the matching section of the string is going to look as follows. So I can visualize it. So everything to the left of the match is the first component of the span in reverse. Then we have the match, and finally we have everything else to the left of the match. So the string which remains to be still remains. And this exactly gives us the boundaries of the match. So two abstract pointers, which mark where the match begins and ends. And this data structure implicitly encodes two locations. So yeah, as I said, the start and the end of the match. The reversal operation on spans is defined by swapping the left and the right components of the span and then reversing the match. Okay, so now the high-level formalization overview. We start with defining the match semantics, which are based on classical language-based semantics. They don't use derivatives, and this is really going to serve as the main specification against which we prove the correctness of our algorithm. We also define the reversal operation and prove the correctness. And this result will be necessary in order to relate the language-based match semantics and the derivation relation, which we define next. And the derivation relation, of course, uses derivatives. And then we show the equivalence between the two representations. We also need to relate the derivation relation to our actual leftmost longest match algorithm. And then we have enough properties in order to prove the correctness of the algorithm. So let's start with the formal definition of match semantics. It is a relation which takes a span and a regular expression, and it tells us when the span is recognized by the regular expression. So it effectively defines the language of the given regex. The first big difference with what you would expect to see is that we're working with spans. So unlike classically where we think of a regex as a set of, the language of a regex as a set of strings over some alphabet, here we have a set of spans. And the match semantics would usually be defined as an inductive predicate with a constructor for each regex. But instead, we define it as a function in the prop, and this was to avoid the non-strictly positive case of negation in our definition. Okay, so just to give some intuition, I mean, the usual operations like the intersection of regular expressions become the intersection of languages. Similarly, negation on the regex becomes negation of the language, the complement of the language. But the maybe more interesting case is the Kleene star, which we encode using bounded loops. So we define this repeat count function, which counts the number of concatenations. Just to quickly recall derivatives, they were introduced by Berezovsky more than 60 years ago. They're used for regular expression matching. And the intuition is that taking the derivative of a language removes a character from those strings that the language recognizes. So an example would be the language which contains the words certified programs and proofs. If we take the derivative with respect to the character P, we get back the language programs and proofs. So certified disappears, which is conceptually bad. And an interesting property of derivatives is that we can have a matching algorithm. So we can repeatedly apply the derivative to the regex with respect to the string, and then the output regex, we check basically if it contains the empty word. And this corresponds to checking if the string was in the language of the given regex. And yeah, working with derivatives is nice because it's defined in a very straightforward way by induction on the structure of the regex. So how is the derivative function defined in Lean? It consists of these three mutually dependent definitions. So the derivative function takes a regular expression and this location. And most of the cases, I mean, again, the intersection of regular expressions becomes the intersection of the derivatives. The case that I want to point out is the concatenation, because there we have to first test the nullability of the left component. And this is exactly where the second function is used. And because of the presence of lookarounds, nullability is conditional, so it depends on the location. And again, nullability tests if the empty word is in the language. So in this case, the empty match. It tests for the empty match. And the lookarounds, the way that the nullability of lookarounds is defined is we have to check whether there exists a match for the lookaround. So this is why we need the third function at the bottom. And exist match takes regex, a location, and it really implements the idea I had on the previous slide, which is we repeatedly derive the regex, advance the pointer in a string, and then basically until we get to a nullable point, which means there exists a match. And also notice that in the definition of nullability, we rely on the reversal operation. So in order to test for nullability of look-behinds, we have to reverse the regex and match backwards. Again, a small example. So a regex C concatenated with the new line character and the string that I have on the screen. So nullability is conditional since, well, R is nullable only if we're at position 2. So we still have to convince Lean that this mutual block terminates. And to do that, we define a custom termination metric. It consists of simpler components, such as lookaround height, the size of the remaining string to be read, and the size of the regular expression. And then we combine these in lexicographic order. And the fourth component is just needed for technical reasons. Lookaround height is just the nested depth of lookarounds. And actually, the definition that I have on the left is not quite what we have in code. The real type of the derivative outputs a pair, the output regular expression, and then a proof that this regex is smaller with respect to lookaround height. And this is needed in order to prove termination for this recursive call in the exist match function, because we rely on the fact that the definition of derivative returns a structurally smaller regex. Okay, so the derivation relation is defined as follows in Lean. It takes a span and a regular expression, and again implements this idea of repeatedly deriving until we get to a point which is nullable. And as I briefly mentioned, the span encodes two locations, the begin and the end location. So although derives takes a span, we can think of it as taking the start location and then moving forward and testing for nullability at the latter location. So we were ready to define the leftmost longest matching algorithm, but I need to introduce two helper functions. The real workhorse is this max match end function, which takes a regular expression and the start location. And you can think of it as returning the leftmost or maximal end location. And dually, we also rely on this min match start function, which takes an end location and then gives us a minimal start location. And sort of under the hood, min match start really just uses max match end, except we utilize the reversal operations. Okay, so the leftmost longest algorithm really combines the two functions that I have mentioned. And the idea is as follows. Right, so the objective is to give leftmost longest match for a given regular expression in a string. So the first function call, we're using min match start, and we want to return the leftmost position in a string. And then from that position, max match end will return the longest end location. So it's easier to explain with an example. If you have the regex AB concatenated with AB star, and the string which contains occurrences of AB. So when we call min match start, notice that we concatenate the regex with top star. This is done because we don't care, we care about where the match begins, but we don't care what follows after. We just need to know where it starts. And then we take this start location and call max match end, which returns exactly the leftmost longest match, which is in this case AB, AB. And notice that it does not return the triple AB match in the second half of the string, because here we're talking about leftmost longest, not longest leftmost matches. Okay. Right, so the main results, the main correctness results, just a quick recap is that, well, if our algorithm returns a span, then the span is indeed a valid match. Okay, now if it returns a span, we also want to say that it is the leftmost amongst all the matches. And similarly, for all the leftmost matches, it is the longest. We also prove the completeness, so of course we want to make sure that if the leftmost longest match algorithm returns fails, then there is no valid match for regex. And here we use the derivation relation, sort of in the proofs of the theorems. Just briefly to mention future work. So we kind of took the bare bones algorithm, but there are many rewrite rules and simplifications which are really tricky. So this is something that we wanted to do, is to prove their correctness. And I briefly mentioned the two works which form the foundations for what we've done here. And formalizing the PCRE match semantics is another challenge because there we have an extra restriction. Alternation is non-commutative. And sort of as a follow-up from that, the .NET NonBacktracking engine relies on finiteness result from Berzovsky, which uses commutativity of alternation. So we also wanted to close that gap and show that in the case of non-commutative alternation, we can still get that result. And of course, extending this work to other features would be an interesting direction. Thank you for listening. That's all for me.
Thank you, Ekaterina. Do we have questions for?
Thanks for the talk. You mentioned that the original paper that you were formalizing gives a linear algorithm. Is that right?
No. So the one that we're formalizing, it's linear if we restrict the length of lookarounds to be bounded. So, but yeah, the lookarounds kind of cause complications. You cannot have linear.
And in addition, you still would need to memorize the inalienability function too?
You mean if the input linearity depends on it, or?
Yeah, even for bounded lookarounds. Because if you just like I know the algorithm for ordinary regular expressions, and there, if you don't do anything with the nullability function, you get a quadratic algorithm.
Right. Yeah. No, I think you're right. It does depend on memoization.
Thanks.
Thanks for the nice talk. I was wondering if you could go back to the grammar. I'm just curious if there are any restrictions on what can occur in the look ahead or look behind. I mean, in
This slide?
Yeah. Okay. I see. As if you support negatives. Have you thought about verifying like capture groups and other features?
Yes, that would be the next direction. But for capture groups, I mean, I haven't thought what the formal semantics would be, but yeah, this would be a potential challenge. No, we haven't started that work.
I see. Thank you.
So I had a question. So here you're showing us a purely functional implementation of the algorithm. Does there exist an imperative version that can be more efficient, or how more efficient is it? And would it be interesting to verify it?
Yeah. So, I mean, there is a gap between the implementation and this. There were some... our idea was to basically start with this and then prove the optimization, because the actual implementation really uses like a lot of rewrite rules and optimization. So there were originally some bugs introduced. So we have some things that we wanted to formalize like in this functional setting. But yeah, at the moment there is the gap between, I guess, I'm just taking the very top level algorithm that is implemented. But
maybe my question is more, what are the programming language features that are used, or like the kind of side effects that are used in the
actual implementation? Yes. You mean if there are other features that I don't have here, or?
No, in terms of side effects, what kind of side effects are performed by the code, if you know about this? They just use arrays and...
Oh, okay.
Or this kind of thing, or?
I'm not entirely sure. I don't want to lie right now. Yeah.
Or if you don't know, that's perfectly fine. Yes, thank you. Do you have one more question, or? Okay, so let's thank Ekaterina again.
Thank you.